Right. Today's topic is within subject designs. I will start this off with the paired t-test, which isn't within subject ANOVA design, obviously, but we'll see that it's certainly related. If you recall from back when you learned about t-tests, there are three different kinds of t-tests. Maybe you only learned two, but that's not important. There's the one sample t-test for comparing a sample mean against a hypothesized mean. That's the one you may or may not have been exposed to. Independent samples T for comparing means drawn from two separate groups, and then the paired sample t-test. This is for comparing two groups that have the same people. So we measure the same people twice. Pre-post designs are very common in that sort of situation. And again, important to know that each have different formulas and different considerations. To highlight the differences between these two tests, with the null hypothesis, independent samples T addresses differences between two groups in a population. And we're really guessing the same thing with paired t-tests, except we have groups made of the same people. Putting an example to this, an independent samples t-test might compare middle school students in Humboldt County from middle school students from Mendocino in terms of where they stand with reading level, whereas a paired test might look at seventh graders and then follow them to the next year when they're eighth graders and see if their reading levels improved. In terms of null hypotheses, Humboldt County and Mendocino don't differ, would be for the independent samples. And then for the paired samples t-test, reading level doesn't change would be a reasonable statement. Here's an example. We've got some data here on knowledge of a topic. And this is just a small numeric example to highlight some calculational stuff. The null hypothesis is that knowledge didn't change. We can see if a formal null hypothesis looks just like the independent samples approach. I would note that sometimes people write this as mu sub d is equal to 0. I don't know where my subscripts went there. That's odd. That simply reflects the average difference score. The calculations, just to give you a flavor of the calculations, I've put the formulas here. The pooled standard deviation is calculated the same as before. The individual standard errors are always going to be the same because you'll have you'll necessarily have the same sample size because it's a paired test. Now, the one place where we differ from the independent samples t-test is in the independent samples t-test, that value for the standard error of the difference between the means that's noted as 2 times R, and then the standard errors. The R there was 0, but here, because we have people measured twice, we can correlate people's time 1 score with their time 2 score. So that's an actual correlation. And regardless of what the number of that correlation is, one thing that you can see in this formula is as that correlation gets bigger, the standard error is going to get smaller, or the denominator is going to get smaller. One of the reasons for this is that knowing 2 data points about somebody, you can predict where they're going to be with a lot more accuracy than you could if you only measured them once. You can see the calculation of the confidence interval and the t-value is exactly the same as before, so no real differences there. All of the differences come from that piece in the standard error, where we see that aspect of variance that can be explained by knowing how somebody scored time 1. We can explain where they might score at time 2. That is, people who scored really high on knowledge at time 1, well, they're not going to get stupider at time 2. They're going to improve relative to their own knowledge. People who were low in knowledge, they're going to improve relative to their own knowledge. So again, we get a lot more explanation of variability by measuring people twice. One of the real advantages of this sort of design. The D statistic is a little bit different, and God, it's another one of these situations where if you could go back in time and find the person who invented the notation, you might want to punch them. The denominator here, S sub x1 minus x2, that looks a lot like the standard error of the difference between the means here. However, note that these are x bars and these are just x's. Why we couldn't have had a better piece of notation here is beyond me. You could have literally picked anything else, and we would have had and we would have had something that would be less commonly confused. Uh, to calculate this value, the standard deviation of the difference between the means, it's a function of the pooled standard deviation, but also a function of the size of that correlation. You can see we have a little formula there for it. Once we have those two pieces, then everything proceeds very straightforward, and we just calculate a D statistic. So again, relatively straightforward approach there. To give you an example of this in a research article, I've got this article by Gomez and then a bunch of other people who are pretty famous, in particular the last two, Sarah Gaither and Cheryl Kyler, both giants in their fields. In this study, they were examining identification with Hillary Clinton both before and after the 2016 presidential election. So the structure of their data is they have a score for pre, a score for post. We use the t-test command, but notice here this differs a little bit from the t-test command we used before. First, for the paired, it's a comma because we're not necessarily predicting one from another. And then we say paired equals true. And then if it says paired t-test, we know that we've done something right. You can see from the confidence interval and the probability that the identification didn't change pre to post election. So again, looks a lot like before. Oh, and also for the LSR, the Cohen's D command, you again see that that comma rather than the tilde, and here you need to say method equals paired.